we talked about different ways of the correlation between data sets. And then I showed this slide where it says correlation is not causation. So if we correlate two things and they correlate quite nicely, that means it does not necessarily show a causation. And this is another example here where you have the strong correlation between sunburn and ice cream eating, but the causation is the hot weather and not ice cream causes sunburn or the other way around. Okay, and so this leads us to inferential statistics. So whereas correlation shows us the relation between two data sets, we often also want to extrapolate, not only describe data sets, but also make some prediction about the future or about regularities of the two data sets and have some generalizations. So say something about what happens in the future, or what happens if the value is slightly changed that we don't have, and so on. So we want to do kinds of generalizations with this data. And correlation is already a step for this, but linear regression is often used for having predictions. So a linear regression, just we have these dots here, and this linear regression would put a line into into these dots such that the error is minimized. So it would put a line here, and this one, the 0 point here would be the intercept. It's called the intercept, and then we have a slope which would be this beta 1 part, and so these are well, two or a couple of more. If we have more variables, we can have more. We would have for each of the variables a beta here that would scale these variables, and put a line here, and then we have one term left over. This is this epsilon. This is the kind of an error, and this line should be fitted such that this error here is minimum, right? And this error here is computed based on the square of the distances between these individual points and that line here. Okay, and so the linear regression would try to fit a line that best fits into these data, into these points. And as the name says, it only assumes that there is a linear relationship between the x and the y. So it would not take a curved or something. A linear regression would assume that there is a linear relation between these two data sets. Now, so this is a little bit similar to person. So previously we had this person correlation, which takes here the standard deviation of, so this is the covariance between the two variables, x and y, and then we have the standard deviation here of the x and the y variable. And this linear regression looks very similar, but only it replaces this y with an x here. So whereas this correlation is symmetrical, this least square, this linear regression is not. Okay, and the effect is something like this. If we have a couple of dots here, and we put this linear regression, so usually you would have these variables that predict something else would then be on the x-axis, and they would be independent, and the y variable would be the dependent variable, because you try to find a line or a relation between the independent variables such that they can predict the output, the values of the y variables, and so y is dependent on the values of the X variable. So usually you would write it like this, okay? So you would like to predict a Y given an intercept here and the slope of the line, okay? Now you could also in principle reverse this and predict the X given the Y, and then you can see here that you see two different lines, okay? So so this is just an indicator that the orientation of the X and the Y is not independent, so it produces a slightly different slope. If we had here a correlation, then it would not matter whether we use this formula or this formula, it would produce the same slope and the same intercept. But because here we don't normalize by the Y factor, it produces two different kinds of slopes, two different kinds of lines here. Okay. In addition, then this is from Wikipedia, I believe. So we assume that there is a linear relationship between the X and the Y coordinates, and so this here, if we have a data set like this, that fits quite well. I mean, there we have this assumption that we can put a line and we have some arrows, but mostly, we can see this relation here between the X and the Y's, which maybe is a linear one. Here, well, if we look at it by eye, we can see this does not seem to be a linear relation, but somehow a non-linear relation, right? So assuming that we have, that we produce this, that we have a linear regression line here is just a wrong assumption. And what would be the remedy? Well, there could be a remedy. One would be we just don't assume a linear regression, but a non-linear regression. There's also packages with non-linear regression, but I think usually, I mean, I believe that's much more complicated stuff, and often people tell that we should, well, it's difficult to use, but one could also have a non-linear mapping of this data points into another plane, so that these data points would appear linearly. Okay, so one could do a pre-processing of the data so that they better fit a linear line. And here we can see that there is maybe an outlier here. So this looks like they all seem perfectly on a line, right? But only there is one outlier here, and which makes that the whole line here, the slope, is somehow distorted, right? So you can see that this linear regression is sensitive to some outliers, which may then distort this whole analysis and the slope of this variable, or the slope of the line here. And here we have another data set where it might be that we just don't have enough data points. Maybe if we collect more data points, these empty spaces here would be filled with other dots, or maybe not. But in any case, it doesn't look like this would be the best. Or maybe there is two processes that have generated the data, this data and this data, and it would be better to separate these, so it could be a bimodal distribution. So we cannot really say very much. Maybe one way to go about this, such kind of data sets, is to collect more data points. Okay, but all these distributions you can find on Wikipedia, and the thing is that the means and the standard deviation and the correlation is all the same, right? So for all these different data sets, these these values are identical, but only and so the line is identical, but the points are differently distributed here and actually imply something quite different, right? Which we cannot see by just looking at the means or standard deviation, or even by at the slope and so on. Okay, so we come to variables. So we have different kinds of variables. We have categorical and numerical variables. And categorical variables, we looked into this already 2 days ago. For instance, text would be a categorical variable, right? We had text 1, 2, 3, 4, 5, 6, and we have participant. We have language. So we had Spanish and Arabic yesterday. Here are more categorical variables, a task, editing or post-editing, right? These are categories. They're not ordered. They cannot be put into an order. Then sex, gender, word class, whether something is an adjective or a verb or something like this. This would be categories. Then we would have ordered categories, ordinal categories, where we can have some kind of an order. So you can say someone is fast or not so fast or slowly or something. And then you could have or middle, upper class and so on, or a large, tall or small, something like this, where you have an implicit order, but you don't really know whether the differences between these different classes here is identical, right? So low, middle, upper class, right? So there can be a bigger gap between lower and middle class than between middle and upper. So yeah, so it's ordered. It's ordered. You can put them into an order somehow, but you don't really know how they fit onto a line, right? Yes, then we have numerical variables, and these are there's distinction between discrete variables, which would be integers. So we have numbers 1 to n or so. So the fixation duration, for instance, we measure this in milliseconds, not in nanoseconds, but even nanoseconds would be discrete. I mean, it looks like quite fluent, right? But in fact, it's discrete. And for that matter, all the variables are discrete because we have a finite number of representation with 32 bits or something. But in theory, we could say there's a discrete numbers and continuous numbers, which would be real numbers. So where we have infinitely many values, at least theoretical possible. And there are all these. Well, we have all these different kinds of variables in these tables from the TPRDB. Okay, so then one can also dichotomize, if this is the right pronunciation, variables. Means we have, for instance, we can, so here it says we have natural categories, sex of participant, gender of words, and so on. But we could also, for instance, dichotomize continuous variables and bin them, like what we had in the histograms, right? So we have a continuous variable, and we can put this into different bins, into groups. And then we can, of course, decide how large the bins are and how many examples are in each bin and so on. But this would maybe make, in some cases, the analysis a little bit easier, but it would take away information, right? So if you say you have 2 types of translators, for instance, experienced translators and novice translators, then you decide by some criteria what you consider to be experienced and novice, and then you have 2 categories. But it would be it would have much more information if you say, for instance, how many years of training they have or days or something, and you would keep that as a continuous variable, and you could then have more fine-grained and a better regression model here. So this is basically what this slide says. So we have these categorical variables have less information, and continuous numerical variables have, of course, more information, because there's so we have a finer grained scale. And here, if you go up here, we have here we have two categories, and in the continuous case we have an infinite number of different values, which would then provide much finer grained information. Okay, and that's okay. So here still there is some slides about modification of variables. So what I tried to say previously, so we can take out outliers. Not everybody agrees with this. So some purists say we should not take out outliers because that's in the data set and we should not manipulate the data. But I think many people do take out outliers, and in particular, you can do this if it does not change the analysis. Means, so you, for instance, you start with a data set and you have some conclusions. For instance, that females are smaller than males, or they have longer hair, or something like this. And then you have some outliers, and you take out these outliers, and still you come to the same conclusion. Well, then you can do this, no, because it does not really change the result, but it becomes more controversial if, when taking out the outliers, the results completely change, right? So before doing this, you could test whether you can do this with no big impact. I mean, it will have an impact, of course, otherwise you wouldn't do this. But if it completely changes the results, maybe you at least one should report this, no? and some findings, and give a reason why, and then you take out the outlier. So, and one way to take out the outliers is based on the Z-score, and that's what we discussed last time, remember? So the Z-score is the standard deviation, relates to the standard deviation, and everything that is 3 or so, well, people have different kinds of approaches there. So 2 or 3 standard deviations away from the mean, you can consider this to be an outlier. And this also coincides with these box plots. So everything that is beyond the ends of the vertical lines in the box plots, that would approximately be 3 Z-scores away from the mean. Okay, then we can also transform the data in different ways. So one can do a root, a square root, for instance, or one can have a logarithmic or exponential distortion of the data. And then normalization. So, for instance, that's also what I showed before yesterday. So we had texts of different lengths. So in natural, so we have, if we deal with texts, okay, so usually texts have different number of words or different number of characters and so on. And of course, if you look into the duration, how long it takes to produce a translation, and it very much depends on the length of the text. If you want to abstract away from this, you could normalize this, right? So you can, for instance, divide the duration. You could look into the duration per word. So you divide it by the number of words, the duration by the number of words. We did this yesterday, and today I showed some examples again. So different ways of modifying variables to find better results, or to better compare different instances for instance, longer and shorter texts or longer and shorter sentences, something like this. Here's an example of duration. So duration often has this kind of an exponential distribution, but we have a very large number of occurrences in the beginning, and then it has a very long tail here, as you can see, right? So this would be, and if we then do a log transformation, it would look like this, which looks much more like a normal distribution. And many of those, for instance, correlation and regression analysis, they work better with these kinds of distribution because they are just look like a normal distribution. The session from yesterday, it's on the server under the summer directory, and I think we came, I talked about this linear regression here, and where we can have a regression line, and I talked about that if we take into account this categorical variable here, the target language, we come to that conclusion that maybe these two languages work differently. But then if we look into the participants, actually, we can see that no, this was an illusion that was based on the fact that there is one very fast translator and the others are not so fast. And this makes that it looks like it look like. So then we have here this R-like representation of the linear regression. And if somebody worked with R, it looks very similar to R, where we have here this formula and the data set. So it means this segment is the data set that we loaded, and perhaps you remember this data set contains sessions from two languages, English into Spanish and English into Arabic, and this would be the formula that that is very much similar to R. Where on the left side, on the right side, right from this symbol here, from this tilde symbol, we have the independent variable, and we want to we want to predict this variable on the left side. Now we can take, in addition, the insertions and the deletions. So we have two independent variables here, and we try to predict this dependent variable here. So we see a clear relation between the number of insertions, here, right, and the duration. But with respect to the deletions, that doesn't seem to add very much. So here the p-value is very high, means that this insertion explains very much the duration, the log duration here, but the number of insertions do not add very much. And so this can be read in addition to, okay, so we can take this out, and then we can have this categorical variable. So as you remember, we have two languages in this data set, and then we can see how these two, the interaction effects we can see with this construct here between the two languages, right? So this TL is the target language, and the C tells the script that this is a categorical variable. It should be taken as a categorical variable, and it will then do this analysis for both these different target languages. And what we can see here is that the intercept for, okay, so we have Arabic and Spanish, two languages, right? And the intercept for Arabic is 5.07, and the intercept here for Spanish is a little bit higher. So we have to add, so this is relative to this intercept here. If we look into this graph here, you can see that this slope is much steeper, as we already saw before, and this is 1.6. So the zero axis would be somewhere here, and if you continue this line here, this guy says okay, if we follow this yellow line here, this would cross the zero line at 5.07, okay, which would be somewhere down here, no? If you follow this, okay, and then this is relative. This intercept is relative to this one. It says add 2.02 to this guy here, to this 5.0. Then we come to the intercept for the Spanish line, which is this blue one. No? So means that the intercept for Spanish is higher than the one for Arabic. And the same is the case for the slope. Here we see the slope for Arabic is 2.03, so this is this slope here. And for Arabic, for Spanish, this is for Arabic, right? And for Spanish, it's not as steep. It's you subtract 1.3 from this number here, and you come to the slope for Spanish, which is then 0.7, something like this, no? That would be this slope here. And you can see here that all these relations are significant. They all have quite small p-values. And this model already explains much better the relation between the variables than this model here, which does not take into account the two different languages. And yeah, so then we can go on, and instead of looking into having this analysis for each language, we can have it for each participant. And we already know that there were 6 participants, right? And you can see if we look into this relation for each participant individually, so that explains much better the data here, okay? And we can see same process here, a little bit more complex. So the intercept of the first participant, this is participant 01 then, right? It doesn't show this here, it's ordered. So the intercept would be 4.9. So this participant number 1 is the green one. Okay, we go further here and we arrive at 4.9. And then for participant number 2, the intercept we would add to this 4.9, 1.09. So this is 6, around 6. For participant number 2, it's the blue one. If you follow this line down here, the intercept would be something like 6. And then for participant number 3, we add 0.7 to this, which would be how much? 5.7, something like this. And for participant number 5, we subtract 1.6 from this number. So that would be 3. How much? 3. That is participant number 5. This one here, this very fast one, right? He has a much lower intercept. And then the same here for the slope. So these things are for the intercept, right? And here, by the way, you can see that these p-values here are quite high, okay? And that indicates that there is not significant difference in the intercept between all these participants and this number 1. Okay, so the intercept, according to this analysis, looks all a little bit the same. Okay, so you can well, you could say that, well, the intercept is like this, but there is no significant difference between the intercept with respect to number participant number 1. And here you can see the slope. The slope here for participant number 1 again is this, the green one, okay? And then you subtract from this slope here these numbers to get to the slopes of these other participants. And here again, we can see that these slopes are all not significantly different. Okay, so that means that in fact, according to this analysis, all the participants have the same ratio between insertions and durations here. So there is no significant difference between those things. Means that you can also see this visually, no? So you see that all these lines are more or less parallel. And if we look into this thing here, we can see that the two slopes are very different. And that's also what it tells us here. Yeah, so the two slopes are significantly different, and we can see this already with our eyes. And here all the slopes are same, so there is no interaction effect, and that's also what this analysis shows us. One can also have much more complicated models. Here one can, so what we did here, we took the normalized version, right? So we said, remember, we predict here, or we we predict the duration for a segment. So, and the segment has different length and so on, so different number of words and so on. And that's why we have normalized this here by the number of target words in the target sentence. Now, instead of doing this, you could also just add all these variables as predictor variables. So here is nothing normalized. We take the whole duration, the duration of the entire segment, and this will be very much depend on the length of the sentence and so on. But all this is taken here into account in the predictor variable. So we have here the number of insertions, the number of deletions, and then the length of the source sentence and the length of the target sentence. Okay, so instead of normalizing these values, we can just take all these variables that potentially would be used for normalization. We could put this as predictor variables. And then the system will figure out by itself which of those variables is the most significant. And here again, we can see in this analysis, okay, same thing, we have an intercept and so on, which is now 40 seconds, almost 50 seconds. And then we have these different kinds of variables. And we can see that here, for instance, the number of insertions and deletions. So the number of deletions does not seem to be significant. So it does not have significant contribution to that whole analysis. So we can actually take this out. So if we take this variable out, we can see that it increases the significance of the insertions. And here we can see, so if we see how well this model explains our data, okay? So we can see this is what this R squared tells us. And if we add again these deletions and you look at this value here, so adding this value actually does not add explanatory value to this whole model. And you can also see it's not significant. This number of deletions is not significant, and it adds no explanatory value. So why would you have it? You can also take it out to make So the goal would be, of course, to have the model as simple and easy as possible with the highest possible explanatory power. Okay. And I think this is what these values also account for. They take into account the complexity of the model, but I mean, I'm not an expert really in regression modeling. So, and this is, yeah, so yes. Okay, so you can have very complicated models, and of course, all this you could also look into interaction effects for each of those variables with the participant, and then you see that you have a huge number of different numbers here and values, and it makes it makes the whole model much more it explains the whole data much in a much better way. Okay, but it makes it also much more complicated. Then another thing that I would like to just very briefly add is that it's also important to look into residuals. So this would be the E. So we explain stuff with the model, right? So this would be the R squared here. And for instance, here we have we try to predict the normalized duration by the source text using the normalized duration by the number of target words. Okay, and this model is explains the data quite well. So we have this correlation here between the normalization of the target by the number of target words and the normalization of the duration by the source text words. So this correlates quite nicely, puts the line, but it does not go through all the points. And then the question is how well, what are the residuals? What remains as an error? What is not explained by this model? And there are a number of ways how to visualize this. Residuals should have normal distribution here, or this QQ plot, they should be quite on this line here. So we can see at the edges here, the model explains less so well as in the middle values here, but it's not so bad. And here, these are the individual residuals and the fitted values. And this plot here should be as homogeneous as possible. It should not have this belly here, but I think this model here is quite okay already, but it would be better even if this was evenly distributed here. Looking into residuals to figure out what whether there is actually some hidden processes that go on that are not captured by this linear regression, by this model. So means if you had, you know, somewhere, if there was a cloud of points here and here, for instance, or it was not evenly distributed, that would be an indicator that actually there's other underlying processes that go on and which are not explained by the model. So, and if it's quite evenly distributed, then you would just have an error in your analysis, but it would not. You don't miss a kind of a process that is not described by your variables. That's my understanding of this analysis. I would like to still look into something else, and which is the pause analysis. So there is, I'm taking this chapter from this book here, and Isabel Lacruz, a colleague of mine, has couple of years, 10 years ago, she approximately, she produced a couple of papers about pause analysis. And this is also, I think, something that Thomas referred to in his what he just said. And in this book, she has this article, Pauses and Cognitive Effort in Post-Editing. And the idea is, of course, a pause analysis, a keystroke pause, a pause where no keystrokes are observed. So we have this key logging, right? And between each successive keystrokes, there's, of course, a pause. Because they don't appear all at the same time. So there's a pause. But so what is a pause analysis? It's a little bit arbitrary. And I tried to talk about this yesterday already a bit. So there's different thresholds what one would consider to be a pause. And this threshold is between 300 milliseconds and 5 seconds. And depending on who you ask and why you would like to do this pause analysis, you'll get different answers. But many people also used about 1 second, and that's why 1 second is the assumption in this TPRDB with these production units, right? So we have these production units, and a production unit is supposed to occur when for coherent typing events when there's no pause of more than 1 second. Okay, so, and why would one do this? And I think the answer is that in these pauses where no keystrokes happen, the assumption is that the translator thinks about the translation, right? I mean, they could also think about their grandmother or whatever, or the food this morning. And so we don't know what anybody is thinking. But if we assume that they are involved in the translation task, the most reasonable or most likely reason why translators don't type is because maybe they think about what to type next. And this is, I believe, the whole idea about pause analysis. And so the idea is the more or the longer the pauses are, the more difficult is the text. So the pauses would give an indication of text difficulty, or maybe, I mean, difficulty is then relative to the translator, our experience of the translator, maybe, and that goes together. How difficult is the text depends on how experienced is the translator with this particular text. And in any case, so there are different ways of address these pauses. And Isabel Lacruz she has a number of different measures here. Introduction here. Okay, so the first measure is this: number of complete editing events in keylog report by number of words. So we assume that there is maybe a piece of text, a sentence, or a text, or an entire text, or a paragraph, or something like this. And there are a number of complete editing events, and there are a number of words. What is a complete editing event? But one can perhaps say that a complete editing event is a production unit, as we have defined it in the CRITT database. So we can look how many production units are there and how many words, for instance, in a segment. Another measure is this total pause time. This is PR pause ratio, I think, total pause time in a segment by total time in a segment. So a segment, yeah, we have segments, of course, in this SG files that I just we just looked into. These would be segments, and we can look into the pause time and the total time. And the pause time would be the time that is not in a translation burst, I guess. Then we have an average time per pause, divided by an average time per word. And then she has this pause to word ratio, number of pauses in a segment divided by the number of words in a segment. And okay, so she establishes these number of different ways of calculating pause, of having a pause analysis on a segment level, and then she puts all this into relation, and she says how those different measures are related and can be mapped onto each other. My conclusion from this, and we use this quite a lot, these different measures, is that the pause to word ratio, this PWR, is the most interesting and the most the measure that predicts best cognitive effort. So where was it? Here. What was it? Here, right? Pause to word ratio. So we have number of pauses in a segment divided by the number of words in a segment. So I want to look into this now and see how we can address this in our data. And there is a script here, number 3, which is called pause analysis. Again, we can load here these libraries. Again, so this is system libraries, this is pandas table, NumPy, and this is for visualization and the linear regression model. And then here we have this interface to the TPRDB. Here is a brief summarization of actually the measures that she showed in the book chapter, and we have these different definitions of these pause ratio, event to word ratio, average pause ratio, and pause to word ratio. Okay, so we want to, I would like to focus on this guy here, it. So what we can do here first is read the segments from this TPRDB. And as you can see here, this function then reads very many different studies here. So we have this BML study. By the way, all these studies are described here on the public study folder. Okay, we have public studies, and then we have these names here of these studies. BML is into Spanish. Here, this one here is from Scratch translation and so on. We have this study, and which one else? So this SG12, this would be German, into German, here SG12. And this is all data from the multilingual corpus. So means that they have all their translation or translations of these 6 texts. Here, this is Chinese, this is Japanese, this is Danish, this is Hindi, and this is Arabic. So we have a large number of different languages, the same texts translated into all these languages by a large number of different translators. And here you can see that we have in this BML study 184 sessions and this number of segments. Okay, so we have for all these different languages here, we have all these different number of segments here. It says what are the languages. So Spanish is BML, German, and so on. So we can see how many sessions there are and how many segments. And we can read this by running this command here and look into the headings. So there are altogether 6,800 segments for all these languages. Okay, so that's what we just looked into earlier today and yesterday too. So it's the same kind of a structure. And here we have these different kinds of features that I was just talking about. This one here is the E session, so this is editing. And if there is no duration and no, so it means that the person just didn't correct anything. We can also, for instance, here look into pick out only the translations. How would we do this? We would say here, task equals T. Okay, and take then the head of this. And the sessions is an S missing here. Okay, so this would then take out from this 6,829 rows, it would only take out those segments that were translated, that were from scratch translated. So if you wanted to look into this, we can also look into how many we have there, and that's, I think, very easily we can do it like this. We can just see that there's 22,800 lines, means there's 2,826 segments that were from scratch translated. Okay, here we can see again that we have these different measures that relate to the translation bursts. So these are translation bursts. So we have for this particular sentence, right? We have 12 translation bursts in this segment, if we assume that the pause is 300 milliseconds between successive keystrokes. Okay, so there are 12 translation bursts, and the duration of these 12 bursts is altogether 10 seconds. And the pause between the bursts is also almost, it's 9 seconds here. Okay, and this pre-gap is the pause before the first typing burst in that segment. Is that clear? Yes? Okay, good. So the same is here the case with the 500 numbers. So we have 12 bursts when we assume a 300 millisecond pause. We have 9 bursts if we assume 500 milliseconds. And then the total of these 9 typing bursts is 12 seconds. And then if we assume a pause of 1 second, we will have 3 typing bursts, and this is the total pause. And so on until 5,000. So we have 0. So means that there was no pause of 5 seconds or longer when producing this this segment. So means that if we have 3 typing bursts here, and the total time is this amount of time for the bursts. And if we add up these numbers, we should always get the same. We should always get the same number. Is that true? If we add up the typing bursts here plus the typing, the pauses, typing gaps, then it would be the same if we separate. No, so there's only is a fragmentation of this whole typing stream in different ways, no, in different kinds of bursts and pauses. That's what this whole thing is about. No, it chops up the whole production time in different ways, in different bursts and in different pauses. Okay, so now we can here compute these different various values or measures that we have. This pause ratio would be, what did it say? Total pause time in a segment divided by the total time in the segment. Okay, total pause time in a segment is this TG. So we will have a different value for each pause duration, right? So we have this TG is the pause time, and then we have this pre-gap, and that's the time before the first typing occurs. So if we add these two together, if we assume that the pause before starting typing is also part of this pause, right? So if it is also in part of that pausing time. If we assume that to be the case, then we can add this pre-gap and the total typing pausing time divided by the duration of this whole segment, right? The production duration of this whole segment. Okay, and here +1 is added because sometimes we will have 0, right? So we had this when we take this out here. Remember, we had 0 also if the duration was 0. If they don't type anything. Okay, so where is the duration, the total duration? Where is it? Here. Okay, so this duration for the production duration for this particular segment was 0 seconds. Okay, and in order to allow this operation here, we cannot divide by 0, so there's just 1 added here. But that wouldn't really falsify much the whole data, because usually these durations are quite long, and if we add 1 or not, it doesn't change much. Okay, so this PRA here then would be the assumption that we have the pause contains the first reading or the orientation before starting typing, and here this B would then be the another way of looking at it. So we subtract this pre-gap here, right, from the duration, and we only take these pauses that are in between these bursts. Okay, so we divide here that we take the total pause duration, 300 based on 300 millisecond, 500 or 1000, and we subtract from this whole duration the first pause, if you like, that precedes the typing in that segment. Then we have, we can write, is there any question with respect to this? We can look into the pause to word ratio. And here the pause to word ratio would be the number of pauses in a segment divided by the number of words in the segment. So we have the number of pauses, the number of pauses in a segment, the number of pauses. Okay, here. So the number of pauses should be the same as the number of bursts, right? So we assume that we have a pause and a typing burst and a pause and a burst, right? So well, there's an alternating between pausing and typing, and so the number of pauses should be the same as the number of typing bursts. Or maybe we can add 1. We can say there's a pause that precedes the first typing burst, and there's a pause that comes after the last typing burst. Then we would have to add 1, or we could just say it's we just omit maybe the first this pre-gap, so to say, and we only count we only consider there to be as many pauses as there are typing bursts. And then we can, and then it says here, number of words in a segment, but this is underspecified whether it refers to the number of words in the source side of the segment or the number of words in the target side of the segment. And so we can have two kinds of pause-to-word ratios. One based on the normalization here on the source, the number of words in the source text, source side, or the number of words in the target side. And we can have this for all different kinds of thresholds, pause thresholds. Okay, so then last thing here is the average time per pause divided by average time per word, and the average time per pause. So we have, this is the time, okay, so this is the total pause, and the average pause would be the total pause divided by the number of bursts, right? So average time per pause divided, so the average time per pause would be this guy here, the number of pauses divided by, no, the total duration of the pauses divided by the number of pauses. And this divided, sorry for this, and this divided by average time per word, which would be, this is the typing duration. So this this guy, this would here then realize a version of this kind of a formula. Okay. Now we can look into this into these values here, what we have produced, and usually here we just add another column into this data frame with these values here, and these values will then are added here at the end. So we have added this PR 300 here, right? So many more columns to this data frame until this value, which is the last one here. Okay, then we can also look into this description, and here we have again the important values for each column, and so the mean, the standard deviation, minimum, maximum, and then the number of occurrences in the quartiles. And here we can see these different values for these statistics. Or we can visualize this with here, for instance, the pause-to-word ratio, assuming 500 milliseconds pause threshold, normalized by the source number of source text words. And you can see here that it's also a quite skewed distribution. Most of the sentences will have a value around here. So more than 1,300 segments will have this value here. And then it has a very long tail, even that you cannot see here below. Okay. Okay, so now we can also correlate the stuff. We have here a correlation matrix, and we can see here how these different pause-to-word ratios correlate. And yeah, so what would be your expectation? I guess the expectation would be that those pause-to-word ratios which are closer together correlate better, and those ones that are further apart correlate not as well, right? So, and this is exactly what we can see here. So all these close by cells have higher correlation values, but the further we go away here, the worse is that correlation. And yeah, the underlying assumption is, of course, that we will have different kinds of processes happening for each pause-to-word ratio. right? So if we assume that there's a 300 millisecond pause, what happens in this 300 millisecond pause, according to Isabella Lacruz? So if translators struggle with motor, so with typing, trying to coordinate the fingers and so on, all this implies pauses, of course. Or if they search for a certain key stroke or for a key on the keyboard and so on, this may be up to 250 milliseconds or so. And what she, I think, says that above 300 milliseconds, there is some kind of cognitive effort. So whereas below, you can't blame motor activities. Now they produce these kinds of pauses. Above 300 milliseconds, maybe we can see some kind of cognitive effects or difficulties and so on. And what happens then with these different thresholds? Yeah, so some pauses are more than 5 seconds or longer, and we would, I guess we can assume that quite different stuff happens in this pauses than in, for instance, pauses of 500 milliseconds. Okay, and interestingly, we can see also that these pauses do not really correlate. So if we take these very long, so well, basically they all correlate somehow, but not extremely strongly, particularly if you take those that are very far apart. Okay, now we can, of course, also relate the pause to word ratio and the number of keystrokes. We can see how does pause to word ratio correlate with the number of keystrokes, and we can go through the same game or analysis that we did before. Here we have a normalized duration, we have a pause to word ratio, and we can see whether these deletions add much more. And here in this case, you can see, yes, there's a significant contribution of deletions and so on.